theoretically leaning material related to the ultrafiltration and the reabsorption mechanism and the nature of nephron, and how basically we can implement this particular knowledge in the implantable kidney. Since it's a tutorial, I will try to interact with the audience in the form of question-answer. So let's pretend that in some ways I am a student, so I'll ask some questions in regards of the material that we already covered during the first 5 lections. First and foremost, are we working? Hold on. Yep. For some reason, we have the extra slide here. I will heavily reference Anita Taylor, the mathematical modeling and renal physiology. If you're interested in that topic, that will be a very great literature to start the exploration. The topic of this tutorial is so broad that it's basically impossible to cover all problems that actually exist in mathematical modeling of the working of native nephron in native kidney, because there are a lot of issues like the active transport, the active ion transport during the reabsorption. There is a lot of issues about the modeling the contour transport in Henle loop, and there are multiple approaches to how actually we're modeling that. But nevertheless, there are some key points that can be emphasized and implemented in different mathematical modelings, no matter what you choose. Because if we talk about, for instance, the solute transport in the Bowman, in the glomerular capsule, basically we can provide some very basic module that can be adapted to isoporous module or heteroporous module, because the different solutes they will transport through the semi-permeable membrane at a different rate. So considering that we covered the topics of the initial physical processes that take place in the Bowman capsule and within the Henle loop, I will take a consideration to ask some questions to the audience, because it's a tutorial, and I think my purpose in that tutorial to interact and establish the feedback with the audience, because it's not like a technical tutorial. We will not discuss any technicalities of how exactly we produce things, but it's more like a seminar where the lecturer interacts with the audience. So in terms of the Bowman capsule, it's of course a very complicated structure that has a lot of different cell types, like the podocytes and other types of cells that allow to perform the initial primal urine formation in the Bowman space. And nevertheless, in terms of mathematical modeling, we can simplify this capillary as just a robust cylinder and a simplified cylinder. Where we assume that there is some length of this particular capillary, and we assume that there is a transport of the flux in plasma, and we have some concentration of a solute in a given space of the x-axis. So what kind of processes can we expect between the capillary and the Bowman space in terms of the flux and solute transport? What particular physical processes we can expect to happen there?
It will interact, okay, so interact.
Yeah, diffusion transport, that's correct. And yeah, osmosis. Well, we will discuss this later when we start assuming the calculation of the solute transport. But in terms of the water flux, can we expect the ultrafiltration here? Yeah. Yeah. So yeah, we can assume that there should be the solute transport and the water transport at very least. And in this initial calculation, especially when we assume can we implement this module in terms of microfluidic system, it would be nice to understand how exactly this process works in Bowman capsule. This module is a very simplified because we assume that it's just a homogeneous membrane, when in reality this membrane is very complicated, and it's better to describe this process through the heteroporous module, etc. So considering the material that we discussed previously, if we assume the process when we talk about the protein flux change, so we're talking about the flux of the protein across the capillary. What value can we assume here considering what we discussed earlier? Well, we made an assumption that this membrane in the first approximation is impermeable to the proteins and the albumin, when in reality, if we talk about the real capsule, there is actually some flux of the protein through the membrane, specifically albumin. But in this approximation, we can assume that there is no difference if we talk about the solute flux over here or over here. That means that there is no transport of albumin across this membrane, and that means that no matter what position of this capillary we assume, there will be no change of this particular description, like QX on CPRX, whereas PR is protein. Speaking of other fluxes, we can actually describe them as follows. So if we assume that there is, let me just rewrite it like this. So there are position x1 and x2, and we want to know how exactly the volume flux changes across the membrane. We can describe it as follows. What is this the radius of the capillary? And that will be a water flux across the membrane. So why exactly do we have to assume this particular value of the water flux? Why do we have to take into consideration this? Yeah, there is a water flux across the membrane. That means that this parameter will not be equal with this parameter at any given moment. And since there is a water transport across the membrane, we need to assume what particular water flux was taking place across this particular distance from x1 to x2. And we can rewrite this particular equation as follows. Up here. And basically, we can rewrite the same thing for the solute flux. So we can assume that if we consider the solutes that can go across the membrane, then we have to take into consideration that will be a solute. And this particular equation can be rewritten as follows. It's going shaky. So to estimate how exactly the water flux and the solute flux changes across the membrane, we have to somehow evaluate the water flux across the membrane, the ultrafiltration flow, and the diffusion and convective transport of the solute across the membrane. Well, usually, yeah, we will discuss it a little bit later. So if we, for instance, try to evaluate what is the water flux across the membrane, and we try to take into consideration all parameters that actually affect the water transport, basically we can rewrite it as follows. So let's assume that will be hydrostatic pressure of plasma, that will be a hydrostatic pressure of the Bowman space liquid. And what other parameters have we taken into consideration when we estimate the water flux across the membrane? Yeah. I'm sorry.
Some effect from the albumin, from the protein.
Yeah, we have to actually assume that there will be an agontic pressure from the albumin. So we have to take this into consideration. Yeah. So we can actually rewrite this as, let's see, it's oncotic pressure of the protein, and we will discuss these parameters a little bit later, because if you consider the previous statement, this parameter should not make any sense right now. But what else in general shall we take into consideration? Should we take into consideration the osmotic pressure in general of some small solutes? Yeah, technically, yes, we have to consider that there is influence of small solutes. And yeah, let's talk about the parameter osmolality. Do you remember what it is? Yeah.
Well, the mathematical formula is minus d delta of del cx by del x, which is basically it's directly proportional to the gradient of the concentration along x.
I think you're trying to formulate the Fick's law. Or
oh yes.
Yeah, we're talking about the osmolality, the parameter that should be considered when we estimate the osmotic pressure, because we're talking about when we talk about the water flux, and there is the the gradient of osmotic pressure, then that basically can be one of the reasons why ultrafiltration happens. Yeah, that's actually a cumulative concentration of all small solutes that, yeah, let's say, and there will be n parameter, and there is the reflection coefficient for a specific solute and the concentration of the specific solute. So it's actually a contribution of all solutes that are dissolved in some solution. In our case, it's a plasma or blood. Yeah. But here we have to take into consideration the difference of osmolalities between the plasma and the Bowman space. So basically, we have to estimate the difference of concentrations of that solute. And right away, we can say what will be the oncotic pressure of Bowman space liquid if we consider that there is no flux of albumin across or any protein across the membrane. Yeah, it will be 0. Speaking of the osmotic pressure of small solutes, we can assume that this reflection coefficient equals 0, and we can assume that there is that this membrane is highly permeable to small solutes. That means that the concentration of these solutes will be equalized very quickly, and we assume that there will be no difference in the concentration of the small solutes. That's why in this estimation we assume that this parameter will be equal 0 as well. And we end up with the equation that we considered right at the beginning of this course. Oncotic pressure in plasma. Oh, thank you. That's what goes for the water transport. We still have to take into consideration the solute flux. So let's quickly look at this particular parameter. Yeah.
You can use that for your
It was for hands. Oh. Oh. Yeah. Yeah. Thank you. I'm sorry. So yeah, let's talk about the solute flux. What particular physical processes will affect this solute flux across the membrane of the capillary? Yeah, diffusion and convective transport, that is correct. It's not like because of just difference of the concentration we have the flux of the solutes, but there is also a water flux that allows to transport some amount of the solute across the membrane. So it's basically the equation of Kedam-Kachalsky. I will not bother you with the justification of how exactly this equation was obtained, but basically we can talk about this. That's an absolute value of concentration, and there is a effective diffusion coefficient for a specific solute. So when we talk about the modeling of the solute transport and water flux, basically what we are talking about the processes that can be described by the ordinary differential equations. So here you can see an ordinary differential equation from which we can derive the parameter of the solute concentration. And this parameter can give us an opportunity to basically describe how the solute flux goes across the membrane. Again, I will not bother you right now with the solution of that equation because it's quite tricky, let's say, because at the end we need to solve this equation. If we just group dy and ds, dTs, so we have a situation when we have the value that we have to describe to the equation, and we have some constant, and that's basically a type of differential equation that can be solved by the Lagrange method or the Bernoulli method. It depends on what kind of route you prefer. It's quite a time, despite the fact that it's not like a very difficult differential equation. It's time consuming, so I will just skip the solution of this equation. But the general idea here is that if we describe the solute and water flux in the native nephron, that's basically the information we acquire to what exactly we should implement and what exactly we should expect from the microchip. And if we know the initial boundary parameters and the initial parameters that we have to achieve, such as the glomerular filtration rate or the solute flux that we have to achieve, what kind of the permeability we have to achieve to gain the exact solute transport that we need, then basically understanding of the simplified mathematical modules is the first step in the modeling of the actual microchip that we have to use, because we basically have an opportunity to apply this knowledge to the microchip knowledge, because that's what we imitate. And at the very end, we have to provide type of membrane that will be very close to the type of membrane that we observe in the Bowman space, in the glomerular capsule, I'm sorry. So I will not bother you with the solution of that equation, and we basically, excuse me, end up with the solution that will basically be, that's a constant that is derived from the further boundary, the Speckle number. And if it's the length, let it assume it's the thickness of the membrane. Where will I? And another constant. And considering the boundary the boundaries of this equation.
This is C1, C2.
Huh? Yeah, that's the absolute concentration equals the plasma concentration at the thickness. Yeah, let me just draw the B1 exponential and Peclet number y divided by the delta plus B2. So basically, it's the condition when we have the membrane and we consider just the one-dimensional diffusion. So if we talk about the thickness of the membrane, for instance, it's a membrane, and that's the capillary where we have the plasma flow, and this is the Bowman space. So we consider, if we start measuring the the y-axis from the beginning of the membrane, right here the concentration of the solute will be equal to the concentration of the solute in plasma at the given position of x. And when we actually cross the membrane, so the y equals delta, that means that the concentration of the solute will be equal the concentration of the solute in the Bowman space. Yeah, and considering these conditions, the constants will be described as follows. And Peclan number, yeah, I forgot about that. That's basically, did I actually write it down? Yeah, one moment. I think there was a something like 1 minus effective. Yeah, that's basically the Peclan number. It describes this particular part of the equation, just to make the writing shorter. Yes. Bowman. Which gives us actually the solution for the CS in Y, and after that we can rewrite the actual the solute flux in a more full form. So let me just write it right there. So basically, the main idea behind this tutorial just to give the common information about that. We have to understand how the solute and volume flux works across the membrane in the Bowman, in the glomerular capsule. And in order to do that, we have to solve the ordinary differential equation that describes this transport. It's a very simplified equation because, again, we consider this particular mathematical formula only when we work with homogeneous membrane. But since the membrane actually is a porous, we have to consider if we solve this equation for some specific solute, if it's is a porous membrane, or if we have to consider the flux of different types of different sized molecules across the membrane, then this equation, of course, will not be enough when we have to solve this particular task for the heteroporous membrane and some distribution modules. But the starting point is to understand the physics behind those processes. So what takes place and how exactly can we describe that in a mathematical manner. And after that, we can actually make these particular equations more sophisticated, considering what kind of task we need to solve and what exact information should we extract from this particular approximation. Basically, the same type of task should be considered when we, for instance, investigate the contour transport process that takes in Henle loop. And in that regard, we need to understand how exactly this process provokes or stimulates the osmosis and the solute transport in the particular system. So we're talking about the Henle loop. And usually what we consider is that the descending loop is the highly permeable for the water flux, and the ascending loop is highly permeable to solutes. And there is another simplification, because usually we talk about the active transport here. So we have the ion channels that basically provide the active transport of the sodium and other ions across the membrane. And usually active transport suggests us that this type of transport requires additional energy. Usually it's adenosine triphosphate, well, that's just a biochemistry, but basically those channels require additional energy to activate the transport of the solute. So the difference between the passive transport, in the passive transport, we do not require any extra energy here. But in this simplification, we consider that it's not like a charged solute, but or ion or a cation or anion, but it's a neutral substrate like urea with no any particular charge. But in reality, the sodium chloride actually dissociates in the water solution, and we end up with the sodium cation and chloride anion. Basically, the main idea why exactly we need to understand this transport is to understand if we can implement this particular type of transport in the microchip technology or kidney on chip, because usually without epithelial cells is quite a difficult task to implement the active transport within the microfluidic system without using any additional fields to create some electrical field that force the diffusion of the electrical charges across the membrane. So basically, there are some simplified approaches to that part. So on the other hand, on the one hand, we can have a system where ascending and descending loop, they are, damn it, I forgot this word. Like they are very close to each other. So they basically, as if they connected to each other, and the first current multiplication loop basically assumes that that there is no water transport in any of these descending or ascending loops, and we actually experience only the active solute transport. And what exactly is off with that particular assumption, considering what I just thought about the actual Henle loop? Yeah, we just made an assumption that there is no water transport in ascending or descending loop. And considering this, what is the difference between this assumption and the actual process that takes in a Henle loop?
Anything, if you clean everything, you can share concentration of chemistry.
What? No, I'm talking about the specific fluxes. So that basically the answer to that question. We experienced we actually absorb the water flux in the descending loop. Basically, it's but yeah, what exactly actually makes it happen? What kind of condition should be met to make sure that we will absorb the water flux over here? Yeah, the difference between the difference between osmotic pressure. So yeah, if we assume, for instance, the descending loop, we actually observe, and that will be, of course, the unit will be millimole per liter, so that there will be constant difference between osmotic pressure in descending loop and the extracellular fluid in the medulla. That's why we actually observe, and since there are aquaporin proteins there, they provide the great transport of water, and at the same time they are not permeable for any solute. So what we actually observe is just the transport of water in the descending loop. But what actually supports the high concentration of solutes in the extracellular space of the medulla?
Whatever you are thinking, you will share it. It may be wrong also, but I probably help you. If you are thinking anything, please not know. So you provide.
Come again?
You don't know for your provide, you may take the specific care.
You're talking about this transport, right?
Yes.
Yeah, that's basically a great assumption. The critical role of the ascending limb is that it's highly permeable for the solids, but at the same time it's impermeable for water. So it's basically a counter-transport process that constantly supports the difference of osmotic pressure in the descending loop and the extracellular space of the medulla. And basically, it's one of the critical parts of the Henle loop of the kidney that basically supports that kind of transport. Of course, we can talk about the vasa recta that has its own transport, and we can talk about the collecting duct that at some point can actually become permeable for urea, for instance, which is a great osmotic agent as well. But it's for that specific conditions have to be met, because in case of the collecting duct, this process actually become prominent when a person suffers from dehydration. So vasopressin actually increases the permeability of the collecting duct of water, and then right at the end of this collecting duct, there are pores that allow the transport of urea and other small solids, usually urea. And urea as a small molecule is a great osmotic agent. But again, the critical role in maintaining this counter transport is behind the ascending loop. All right. Now let me see. So in the first assumption, when there is a modeling of the Henle loop, so this is a descent loop, and this is the ascent loop, and they are so close to each other that the transport of the solute goes across the membrane, so it does not end up in the extracellular space. So here we make an assumption that the descending loop and ascending loop are impermeable for water, unlike in the real Henle loop. That means that if we talk about the volume flow, let it be F descending loop volume, and we have some position over here and some length of this loop. We assume that this parameter does not change And the same goes for for the ascending loop. And speaking of the solute flux across the descending limb, it can be described as follows if we actually consider the equation that we were talking about at the beginning of this tutorial. So yeah, we're basically talking about if we just simplify this limb like this, and there is some length, and we consider x1 and x2, and we try to estimate how the flux flow changes. This parameter will not change because we're assuming that this particular membrane is impermeable to water. Then we have to take into consideration that we look how the flow of the solute changes across the membrane, and we're considering what we have in position 1, x1. And if we assume that there is a flux of the solute across the membrane, then of course we have to take into consideration this flux as well. And basically this is how we acquire this particular equation. So this is our first assumption. Yeah. Well, if the flux goes to this descending limb, that means that the descending limb actually acquires the solute that goes from the ascending limb. And we assume that there is no interspace between them. So in this case, we actually sum this parameter because we actually have the influx, not the opposite. It does not go in the opposite direction. If we describe this for the ascending limb, then yeah, we assume that this parameter should be with minus. Yeah. No, this considered is for the descending limb. The same assumption goes for the ascending limb. That there is no water flux. And in case of the and in that case, we can simplify this as the parameter minus a. And we assume that there is a direct flow between this ascending and descending limb. That will mean that right at the bottom of this loop, we will have the flux parameter. And another boundary condition goes for the beginning of this loop at the point 0. Since there is no water flux, we will assume that across the membrane, we will assume that there is some initial parameter that can be described as water flux at 0. So and basically, yeah, let me just find my scribble here. When we solve this system and we consider, we try to predict how the concentration of the solute in the descending loop and ascending loop will change, we basically skip the long part again because of the time constraints. So considering these boundaries, we can estimate the concentration of this solute. In the ascending and descending loop in the following manner. Which will actually end up with the following.
What is represent
F, that's volume, that's comma 0. That's the water flux right at the beginning of the descending limb. So this module actually predicts that the solute concentration will be the concentrations in the ascending and descending loop. They will be equal in any given position of X. The solute concentration increase along the X, and the larger the loop will be, the higher the loop band concentration will be right at the end of this loop. That's the very simplified version of the counter transport module. Basically, I will shortly describe other approaches, because basically, if you start scanning through the materials that describe the mathematical background of the current transport measure, there are different approaches for that. So, of course, it's a very simplified module. Basically, what we have to consider in more precise models, so to speak, we have to consider that there is some extracellular space between descending and ascending loop. And we consider that descending loop is the permeable for the water, and the ascending loop is the impermeable to water, but it's permeable for solute transport. That will be solute. And in this module, considering the simplified version of transport, we can actually acquire a more accurate description of how exactly the counter transport works through the estimating how the concentration of the specific solute changes in the extracellular space, because we assume that there is a solid transport here and here, and the concentration will be affected by there will be a transport of the solid over here, and there will be a transport of the flux over here. And both those parameters will affect the concentration of the solute in the extracellular space. And we assume that if this descending loop affects so permeable to water that at any given position of X, the concentration of the extracellular solid will be equalized with the concentration of the descending loop, of the solid in the descending loop. And this basically provides us a better understanding of the countermeasure, but this simplified version is the start that provides basically giving a better understanding of the mathematical background behind this process. And of course, if we go even further, we have to consider that there is basically a collection duct that basically participates in the mass exchange process as well. This is the central module, core module, and here we assuming that there is no extracellular space between the cross section between the descending loop and the cross section. So we consider the transport and solute transport, taking into consideration that there is the water flux and the solid flux and the collecting duct. And that basically provides another explanation how the concentration of the solute can change at any given position of X. So why exactly do we need to basically understand the mathematical module of the processes that take place in the native nephron? That's basically the key to understanding of what exactly we have to assume and what kind of microfluidic system we have to develop in order to imitate the basic filtration in the Bowman space and the current transport, and whether current transport will be possible in case and how it will be possible in the microfluidic system. So we basically need to figure out how to imitate the current transport in case of the microfluidic system, or considering the possibility of building such system. But before that, like even the basic mathematical module is basically required for a better understanding of the physical processes that take place in the native nephron. Yeah. Considering that it's a huge topic, I will reference basically the mathematical modeling in renal physiology by Anita T. Layton, and the very detailed article about the transport, a modular and reusable module of epithelial transport and the proximal convoluted tubule. That's basically a very good explanation and very thorough explanation of what mathematical problems should be solved in case of understanding what happens in a native nephron. And in my opinion, it's a good start to actually to provide a mathematical explanation on what we have to expect in the microfluidic system and what parameters of membranes and in the hydraulic system we have to take into consideration to imitate the processes that take place in the native nephron. Thank you for your attention. If you have any questions, I will be glad to ask them, to answer them.
If there are different solutes, there are different molecular weights, different mass, different size. So as a whole, how to find out the equivalent flux as a whole? So you
Well,
calculate for 1-to-1 and then average.
For that purpose, I think it's required to use the heteroporous module where we consider the different permeability for different sized molecules. I think that's the fastest and easiest way to module this process, although it might be not that accurate because we have to consider how the concentration of a solute will change within the membrane, because the transport will go through the membrane and some solute will be absorbed in the volume of the membrane. But a good start would be a heteroporous membrane approach. So we just consider the distribution of different sized pores that provide a different diffusion transport or convective transport through across the membrane. That will be a relatively accurate approach that basically will give us a better understanding of how different solutes will go through the membrane.
So, so what is the actual things in the human glomerulus happens that is a heteroporous approach?
Yeah, the membrane itself is a very complicated structure, considering that there are some podocytes that have actually charge, and those charges also affect the transport. Like some negatively charged proteins cannot penetrate the membrane. We have to take into consideration that there are some protein-bound toxins that also eliminated during the blood filtration, and basically nephron can allow the transport of this particular protein bound toxins through the Bowman capsule, while there are some complicated processes that take place in case of the deproteinization of these particular toxins and the further filtration. It's basically, yeah, the cellular structure of the nephron is a quite complicated topic, and of course it's very hard and I think even impossible to cover all particularities of this difficult structure. But nevertheless, there is still an opportunity to make a simplified module that gives the basic and better understanding of what processes take place. Yeah.
In nephron, all the filtration process in nephron only. Filtration process, filtering process is the blood filtering process in nephron.
You mean the blood filtration?
There is two lips, one descending and ascending.
Yeah. Well, nephron actually provides.
In this structure, there is S2 is this side. So my question is, urine is filtering at this side and the blood, what the actual means actually?
Well, the formation of primal urine happens in the Bowman capsule, and this particular part actually describes the reabsorption of water and nutrients in the descending limb and the ascending limb. Because if we had only a passive filtering blood filtering, and we had only this structure that provided this kind of filtration, that means that if we take into consideration the glomerular filtration rate, we would just go dehydrated in the matter of 30 minutes or even less. So the structure of the nephron provides the reabsorption of the water and the essential nutrients that are required for the human organism. And speaking of other structures, there are also the vasoreactor and the capillaries that actually provide the transport of nutrients and water as well. But the overall blood filtration and reabsorption process takes place in kidney, is the main homeostasis organ of human organism.
Any other question? Please interact. Any other?
Yeah. Mm-hmm. Mm-hmm.
They are also taking similar parameters.
Well, I think that they can use this similar approach because we have still to assume how the water flux will change across the proximal or distal tubule, how the solute transport will change, and what particular processes will affect those parameters. So basically, we can start from the same starting points by simplifying those tubules in the form of robust cylinder and just working with the most simplified approach, and then we can make a more complicated module that provides a better understanding behind these parts of nephron.
So thank you very much, Dr. Boris, for
Thank
your
you.
wonderful tutorial presentation. So it is just like a one in the classroom teaching. So he was writing everything, explaining the complicated equation, complex equation, microfluidics equation, and really, I think I think all the students have enjoyed and understood that what you mean to explain. So it is a very well explained and easy to understand also. So today we have ended up this today's session. So tomorrow we will come back with another three lectures. So tomorrow maybe I have one lecture tomorrow, one session I will take, and another two sessions will be taken by the Dr. Boris. Okay. So far we are closing now today's session, and I think there is a cup of tea is waiting. Naidu. So there is a cup of tea for all the participants. Please have a cup of tea. Okay, and come back tomorrow with more charged. Okay, and more enthusiasm and spirit. Okay, and also bring others. Okay, all the other participants, your friends. That I think the day by day the session is going to be more interesting. But you will be learning a lot of things. Okay, so slowly actually. So Boris is designed in such a way the full course is so beautifully. So first introduction, overview, then slowly mathematical modeling, then slowly he's moving into the deeper side, and the most important that the technology implantable kidney on chip the technology. So thank you very much for your nice presentation and lecture and tutorial session today. Thank you all. Okay. Yeah. Just have a good round of applause for Dr. Boris. So